In the last section of Chapter 6, we're going to look at comparing two populations. So comparing two proportions based on random sampling or randomized experiment is a very common situation encountered in statistical practice. So what you're trying to determine is whether two treatments caused the observed difference, and you want to draw a conclusion about the population for all subjects. So we're going to kind of go back to when we were talking about sampling distributions for a difference in proportion. So just to kind of recall, the shape is approximately normal. As long as N1 P1 was greater than or equal to 10 and N1 times 1 minus P1 was greater than or equal to 10. And then also N2 P2 had to be greater than or equal to 10 and N2 times 1 minus P2 was greater than or equal to 10. Our center, so the mean of P1 hat minus P2 hat, was just P1 minus P2, as long as both distributions were random. And then our spread, so our standard deviation formula, standard deviation of P1 hat minus P2 hat, was the square root of P1 times 1 minus P1 all over N1 plus P2 times 1 minus P2 all over N2. And again, for that, we had to check independence for both. So N1 had to be less than or equal to 10% of its population, and N2 had to be less than or equal to 10% of its population. So those conditions are going to come back and play a part for not only confidence intervals for a difference between two proportions, but also in a significance test for a difference between two proportions. So we're going to start with the confidence interval. So just to kind of review, in general, a confidence interval is your statistic plus or minus your critical value times your standard deviation. So as long as the conditions are met, the confidence interval for a difference in proportions, P1 hat minus P2 hat, is P1 hat minus P2 hat in parentheses, plus or minus our Z critical value times our standard deviation, P1 hat times 1 minus P1 hat all over N1 plus P2 hat times 1 minus P2 hat all over N2. So the way we calculate our critical value is the same way we did when we were looking at a single proportion. And now, instead of it called a one sample Z interval, it's now called a two sample Z interval for a population proportion. So the process to calculate the confidence interval is the exact same way for a difference as it was when you're looking at a single proportion. And you have to check all of your conditions as well. So let's go ahead and look at an example. So as part of the Pew Internet and American Life project, researchers conducted two surveys in 2012. The first survey asked a random sample of 799 U.S. teens about their use of social media and their internet, and a second survey posed similar questions to a random sample of 2,253 U.S. adults. 80% of teens and 69% of adults used social networking sites in these two studies. Construct and interpret a 95% confidence interval for the difference between the proportions of all U.S. teens and adults who use social networking sites. So similar to when we were looking at a difference in proportions, the first thing I need to do is define what my P1 and P2 are going to be. So P1 is going to be my proportion of teens who use social media sites. And P2 is going to be the proportion of adults who use social media sites. Now I want to check my conditions. So we'll start with random, and it does say for both that they did a random sample. Next, we want to check independent. So 799 needs to be less than or equal to 10% of all U.S. teens, which there's at least around 8,000 of those. And then 2253 has to be less than or equal to 10% of all U.S. adults, which there's at least 22,000 of those. And then for normal, 799 times 0.80 has to be greater than or equal to 10, and 799 times 0.20, which we're definitely good there. And then 2253 times 0.69 has to be greater than or equal to 10, and 2253 times 0.31 has to be greater than or equal to 10, which again, we're good there. Now I want to start setting up my confidence interval. So I need to calculate my Z critical value, which if I go to INV norm, because I'm 95% confident, my area would be 0.025 because I take 5% and divide by 2, mean and standard deviation of 0 and 1, and we'll get 1.96. So now I'm just going to plug in all of my statistics into my formula. So P1 hat is 0.8 minus P2 hat 0.69 plus or minus 1.96 times the square root, and then we'll do 0.8 times 0.2 over 799 plus 0.69 times 0.31 over 2253. So start with 0.8 minus 0.69, and that's going to give us 0.11 plus or minus, and then I'm going to go ahead and do my critical value times my standard deviation all at once in my calculator. And we're going to hit 0.0337. So 0.11 minus 0.0337 is 0.0763, and then 0.11 plus 0.0337 gives us 0.1437. So now I have my confidence interval. So for our sentence, we are 95% confident that the true difference in proportions of teens and adults who use social media sites is between 0.0763 and 0.1437. And then if you want to use the calculator to calculate your confidence interval, so you still have to write what the formula looks like, but if you go to stat and then tests, and then you actually go to B, so stat, tests, and then B, that's where you see the 2 prop Z int. Now here's the problem here is that you need X1 and N1, and we weren't actually given an X value, we were just given the percentage. So I would have to find 80% of 799, and if it's not a whole number, then I'm running into rounding issues and my interval isn't as accurate. It works the same thing with x2 and n2. I was given a percentage and I'd have to find 69% of 2253. And again, if it's not a whole number, then I have to round and my confidence interval isn't as accurate. So if you're given the percentages, it's more accurate and better if you go ahead and use the formula. But if you're actually given an x1, n1, and then an x2 and an n2, you can either use the formula or the calculator to get the confidence interval. So the last thing we're going to talk about is a significance test for a difference between two proportions. So your null hypothesis, so the conditions are the same thing. We'll do random, independent, and normal, just like for confidence intervals, and then you can do your significance test. So in this case, the null hypothesis is always going to be that P1 equals P2. Another way you can see it is that P1 minus P2 equals 0, so that there's no difference. And then the alternative hypothesis is then either greater than, less than, or does not equal. So they're either the same, one is bigger, or one is smaller. So when it comes to our test statistic, so our test statistic Z, we're going to do P1 hat minus P2 hat, and then minus 0, because P1 minus P2 is 0, over, and then we have to use something called a pooled proportion. So it's PC times 1 minus PC over N1 plus PC times 1 minus PC all over N2. So this is where we get a little bit different than our confidence interval, or even our distribution, our significance test for a single distribution. So, sorry, they should have hats on them. So PC hat is something we called a pooled sample proportion. So we use this because we're assuming the null hypothesis of no difference is true. So we have to take all successes are going to come from the same pool. So the pooled proportion only takes into account the successes from your two distributions and finds a new proportion based on that fact. So the formula for PC hat is x1 plus x2 over n1 plus n2. So that's how we find our pooled proportion. And then to find our p-value, we use normal CDF like normal. I will also discuss the calculator feature as well. That will help you calculate it for the difference in proportions significance test. So this is called a two-sample z-test for a population proportion. So for our example, we have that researchers designed a survey to compare the proportions of children who come to school without eating breakfast in two low-income elementary schools. An SRS of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, an SRS of 150 students included 26 who had not eaten breakfast. More than 1,500 students attend each school. Do these data give convincing evidence at an alpha of 0.05 level of a difference in the population proportions? So let's start by defining our P1 and P2. So I'm going to have P1 be the proportion of students from School 1. And then P2 is going to be my proportion of students from School 2. For our null hypothesis, it's going to be that P1 equals P2. And for the alternative hypothesis, because we did not specifically state whether or not one school has a lower proportion or the other one has a higher, we are looking to just see if they're different. So P1 does not equal P2 is our alternative hypothesis. Now for our conditions. So we start with random, and we did take an SRS from both schools. For independent, 80 has to be less than or equal to 10% of all students from school 1, which they did tell there's at least 15, there's more than 1,500, so there's definitely more than 800. And then for our second, 150 has to be less than or equal to 0.10 of all students from school 2, which there's more than 1,500, so we're good there. And then for normal, we're going to do 80 times. Now I don't have my P1 and my P2 hat yet, so I'm going to go ahead and calculate that up here. So P1 hat is 19 over 80, which is exactly 0.2375. And then P2 hat is 26 over 150, which isn't exact, but we're going to go 4 decimals to keep in line with our first probability, 0.1733. So we do 80 times 0.2375 has to be greater than or equal to 10, which it's going to be 19, so we're good there. And then 80 times 0.7625 is greater than or equal to 10. We're good there. Then for our second group, 150 times 0.1733 has to be greater than or equal to 10, and it's 26. And then 150 times 0.8267, which is definitely going to be greater than or equal to 10. So all of our conditions have been met. So before I go ahead and calculate my test statistic, I need to find my pooled proportion. So I have P1 hat and P2 hat, and now I have to find PC hat. So I have to do 19 plus 26 over 80 plus 150, which gives us 45 over 230. Which is a proportion of 0.1957. Again, not an exact decimal, but I want to be consistent and around the same decimal places I did before. So for my test statistic, we're going to do P1 hat, 0.2375 minus P2 hat, which is 0.1733, over our pooled proportion, 0.1957, times 1 minus that, which is 0.8043 over N1, which is 80, plus our pooled proportion again, 0.1957 times 0.8043 over our second sample size, 150. So I'm going to do this all in one step in my calculator, just so I get the most accurate answer as possible. And then I'm going to go over how you can do this using the test in the calculator. So we're going to get a z-score of 1.17. So now I'm going to go to normal CDF. And because I haven't specified in which direction, and it does not equal, I use the sign of my z-score to determine what my lower and upper bounds are. So my lower bound is going to be 1.17. My upper bound is going to be 1E99, mean of 0, standard deviation of 1. And we're going to get 0.121. Now remember, whenever our alternative hypothesis does not equal, we have to double this p-value because I could have been above or below. I have to do that combined area, which means I get a p-value of 0.2420. Now I want to compare this to my alpha, which is obviously greater than 0.05. So whenever your p-value is greater than alpha, you fail to reject your null hypothesis. So for our sentence, we say, we do not have enough evidence to show a difference in proportion between the two schools. So if I wanted to do a 2 proportion z-test in my calculator, which is the last thing I'm going to talk about, the calculator steps are written right here. So again, you're going to go to Stat, and then you're going to go over to Calc. Tests. And then number 6 is a 2 proportion z-test. So it asks for x1, n1, x2, n2, and then your alternative hypothesis. So in this case, I can go ahead and use this feature because I was specifically given an x1 and an x2. I wasn't just given the percentages ahead of time. So x1 would be 19, x2 would be 80, n1 would be 80. X2 is 26, N2 is 150. Then I would select the does not equal P2, and then I hit calculate. So it gives me my z-score, which is a little bit more accurate, but to 2 decimal places, exact same that we did. It gives me my p-value, which is a little bit more accurate. It's actually 0.2427. Now here's the nice thing. If you use the calculator to function like this to calculate your p-value, it doubles it for you already. So you don't have to remember to double the p-value if your alternative hypothesis does not equal, which is nice. It gives you your p1 hat, your p2 hat. They call the pooled proportion just p hat, and then n1 and n2. So no matter which method I use, whether or not I calculate the z-score and then use normal CDF, or I use the calculator to calculate my p-value, I still am going to fail to reject my null hypothesis. So again, not a difference that makes us change our conclusion, so it doesn't matter which one you use. And then there's just, again, how you do your 2 proportion z-interval, which we didn't do for our example, mainly because of the chance of decimals. So let me know if you have any questions about performing a significance test for a difference in proportions or calculating a confidence interval.